I think we'll get started. Good evening, everybody, and nice to see a full house. It's a pleasure to welcome and introduce Professor Ananthanarayan. He's in the Center for High Energy Physics in IISc, and he studied chemical engineering in IIT Madras and then moved to US for his PhD, then a couple of postdocs in Switzerland, and then he started his lab in IISc where he has been for 30 years now.
Little less. Yeah.
Little less. It's for the experience there. So along with this, he has also been spending a considerable amount of time in thinking about these questions and the joy of discovery that we tend to forget in the daily grind of science, right? And I'm really happy to see a lot of students from other colleges who have come here to understand what joy means in science. So Anant is also been, he has a lot of credits. I'm not going to go in a lot of detail. He has won a lot of awards that we can all look up. But what I also learned is that he has been advising the government of India also for matters relating to international collaborations, particularly like the CERN in Switzerland and so on. We are really happy to have you here, Anant, and looking forward to this very exciting talk.
Yeah. Thank you very much. Thank you all for being here. As Varada said, I've been here for nearly 30 years. It'll be 30 on December 4th of this year. And it's the first time I'm actually entering this institute in any kind of an official capacity. So it's really a momentous occasion for me. Just a couple of comments that I want to say before I start this talk. What is really going to be important is an interaction with you and whatever the questions that you may have. If you have any anxieties, which undoubtedly we will have about a career in science, that's where I'd like. So I'd try to keep this talk relatively short and succinct. That said, there is something known as cognitive stress associated with trying to learn anything new. So this is a feature of education and of the human brain. So I just request you to, kindly bear with me during these 50 minutes or so that I plan to talk about this subject. There are many things that you obviously know already, but I'm going to try to pose many questions while I speak about this particularly important matter. It's particularly important at this time because the world is in a state of turmoil, and many of us are being asked, why do you have to do science? What is it good for? Then there are the pressures coming from AI and ML and Anthropic and Axiom and all kinds of things, which threatens to make every one of us redundant or irrelevant. So it is a kind of an important moment in history. So let us take a second to think about that while we go on today. There was a person who was a theorist of talks, how to give talks. Patrick Winston is a professor at MIT. So he has many beautiful YouTube conversations on how to give talks. Unfortunately, I'll be violating some of his principles. So he has said that we have only one language processor. It's either auditory or it is visual, and not both. And this is obvious. If you're looking at your cell phone, you obviously don't hear what your mother is saying. So it's kind of obvious. So his advice is not to overburden your slides, but unfortunately the topic today is kind of complicated, and so I'll have no choice. So I'll try to set the stage, just talking a little bit about things that you may know already. I'll have frequent references to anecdotes, just as placeholders, not necessarily because that's the most important thing, but just something that you and I can both relate to. For instance, I'll occasionally mention Nobel Prizes, because Nobel Prizes are very popular. Everybody knows about them. Doesn't mean that that's the only important thing. So please don't go away thinking that this is a talk only about Nobel Prizes. And no active scientist, including Venki Ramakrishnan, believes that Nobel Prizes are the aim of science, at least for most of us. So let me begin as warm up a little bit, and because this is the National Center for Biological Sciences, subject about which I actually hardly know anything, but I will have a few slides essentially from the point of view of a layperson in this particular topic. Let me start with these words of a very famous mathematician who lived in the 19th and 20th centuries. His name is David Hilbert. So he said, and these are some of the most impressive words that I know. So he said, we must know and we will know. So here are two things. So we must know is an urge, and we will know is an imperative, that we will make sure that we know. So in my mind, this is one of the most important things that actually drives working scientists. that nobody else except he or she understands that this really is the reason for the motivation for doing what it is that we do, even though the rewards and so on are not so great, and monetarily, of course, we are all broke, but that's a talk for another day. Yeah. So just don't want you to go away thinking that you'll only see pictures of men. So I'm also going to show some pictures of women. And this is a woman whose name I will not say now, but it'll show up in one of the slides. And this will be a challenge for you all to stay awake so that you don't miss knowing the name of this person. Anybody here knows her name? Oh, good. Okay, fine. So now that keeps the suspense. So I'm sorry, maybe we can turn off this light, because then, of course, it would also lull people to sleep a little bit. Otherwise, there's something wrong with the colors that I've chosen. It's not looking so nice. So I'll also read out what's written over here. So this is called black hole horizon, as seen by a telescope that is called the EHT, which is the Event Horizon Telescope, which looks something like this, which in the Western world would be a donut, while it is vada in our part of the world. So this is a computer-generated image from a lot of data from various observations, and this represents matter falling into this center of this object over here, and this is various gases around it which are being heated, and this is said to be consistent with an object, a very pristine object whose existence was predicted by the Einstein theory of relativity over 100 years ago. It's known as a black hole, and there are many black holes in the universe, but obviously seeing them has to be only indirect, because a black hole by definition is something that you cannot see. You can only try to find evidence of black holes by looking at surrounding matter. We know that many galaxies have black holes at the center of the galaxy, including ours. We have a supermassive galaxy. However supermassive it may be a million solar masses, it's nothing compared to the mass of the galaxy itself, which is of the order of billions and billions. But that said, today we know that black holes are very common, something very esoteric predicted by a very abstract mathematical theory. Nonetheless, it is visible today, visible within quotes, through indirect observations such as the one that I'm talking about. There's another marvelous prediction that was made by Einstein theory, even though he didn't really believe that such a thing would exist, or rather that such a thing would ever be detectable, and this is called a gravitational radiation. And we have actually seen gravitational waves today through human ingenuity, constructing essentially telescopes using a variety of techniques, and we have actually seen gravitational waves. And there was a momentous event already about 10 years ago, I think it was, when there were these two stations in two different places in the US, one in Louisiana, which is in the southeast, and Washington State, which is in the northwest part of the country, separated by thousands of kilometers, and both of them had to work in sync in order to be able to prove definitively that gravitational waves have been seen, which were produced in a massive collision long ago, about 1.4 billion years ago. Well, that's also the population of India, but just as a number, just to keep in mind. So we are also small, one part in 1.4 billion, and to each one of us, we are quite important. So please don't feel belittled by numbers like 1.4 billion years. So I'm also going to challenge you a little bit mathematically, and I'm going to tell you that there were two black holes which merged in an enormous kind of collision. One of them was 36 solar masses, and another was 29 solar masses. And someone has to tell me what 36 plus 29 is. That's 65, and it was 65 even 1.4 billion years ago. But the new object that was formed was 62 solar masses. So let me ask you, what's the difference between 65 and 62? It's 3. So what happened to those 3 solar masses? It just disappeared into energy, right? Into gravitational waves, which basically shook the entire universe. So you have to think of it that way, not just in terms of words, gravity waves. Imagine shaking the whole universe. But that's what it does. But now we have seen many, many more such collisions and mergers of black holes. We've also seen mergers of neutron stars, which in the ambience of these neutron stars, in that explosion, they produce all kinds of heavy metals, which are still present in today's universe. So just think about what science is, enormous distances, elements, matter whose signal you're seeing in various parts of the electromagnetic spectrum, the gravitational waves. That's what science is, and this is what makes it fun to do. But these things are not just done by people sitting in other countries. There are scientists in IUCAA in Pune who contributed very much to understanding this. We have a colleague in Raman Institute, recently retired, now at ICTS, which is a sister organization of the NCBS, Bala Iyer, who's one of the great experts on this, who has contributed in a fundamental way to computing properties of black holes. See? So these are people amongst us, just like you and me, a bit smarter, but let's not tell them that. So now, as of the budget the other day, where Madam Finance Minister has said she's also going to support a third station of these experiments, which are called LIGO, Laser Interferometry Gravitational Observatory. That's what it's called. And India is going to have a station also, and somewhere in Maharashtra, not so far from us. So this is a place for you to visit in future. And this also led to an amazing Nobel Prize to the pioneers of this whole enterprise of building these gravitational wave detectors. Just to tell you, Kip Thorne, he started working on this roughly in the year 1970. Okay, so he, plowed a lonely furrow for about 40 or 45 years till his dream came through. These are also other pioneers, experimentalists who worked on this. But this person, he was also young once. This is his picture. I too was young once, but nobody knows. This was Einstein when he was rather young, when he was about 26 or so. And here are some comments that he makes. And each one of the things that he says here says something about him. So he says, I was sitting in a chair at the patent office in Bern when all of a sudden a thought occurred to me. If a person falls freely, he will not feel his own weight. I was startled. This simple thought made a deep impression on me. It impelled me towards a theory of gravitation. There's a history in everybody's life, particularly people like him who also lived in troubled times. So why was he in Bern? Because he was born in Germany, but he went to school in Switzerland, and later he had to get a job. But he didn't get an academic job because for some years he didn't have proper papers. So it's not just a matter of ICE knocking at your door or being an illegal immigrant, but this is as old as history. For some time he had no proper papers, kind of stateless, and he had to keep applying for all kinds of things. So no job. So he had to work at the patent office as a clerk. And there are many pictures of him standing at a lectern like this, because I guess he had to stand and read the applications of patents. But the good thing about working at the patents office is he learned to be critical about things, and he had to figure out whether an idea actually works or not. So he really had this kind of practical training when it came to thinking about things. Does it make sense or not? So the story goes that Switzerland, as you know, is famous for clocks and watches. So this idea of simultaneity, which is very important in his formulation of the special theory of relativity, they say it occurred to him because he would be observing different clocks in different towers. Well, these are all urban legends, but this is what makes our subject interesting. So one of my former students, who is now a professor, has walked in late just as he did 25 years ago, but anyway, so let it be. Yeah. So, okay, so there we go. So this was Einstein. This is another amazingly famous person, rather aloof person, S. Chandrasekhar, who also had many observations about what is science, what makes science interesting. And he's also had an eye for beauty and aesthetics, and he has written massive books on every single subject that he studied. So he says this, and there's something to think about. He says, in some strange way, any new fact or insight that I may have found has not seemed to me as a discovery of mine, but rather something that has always been there, and I had chance to pick up. So he's saying that physical reality is actually out there, and you just have to go out and discover it. This becomes a little more complicated in mathematics, because often there's a question: do mathematical objects exist, or are they a creation of the human mind? But if you ask mathematicians, they'll say that they do exist, and we are just out there picking the low-hanging fruit, or also the not so low-hanging fruit. So that's Chandrasekhar. So many people have thought about this, and if you want to pick, create a comprehensive picture of what is the nature of knowledge, what are epistemological questions. There are a lot of things to read, okay. But the point in the case that I'll make is that most of these actually come from essentially the West, what you may call the metropolitan centers of science, while we in India have not really done enough work about these things. And one of my pleas to you all would be that you must take up this challenge, because probably our generation is already kind of finishing up its innings. So when you're talking about science, what is science? Science is basically understanding, first of all, the inanimate nature from the smallest length scales. Today we think that matter is made of indivisible constituents called quarks, which make up protons and neutrons and so on. And those in turn will make up nucleons, which in turn will make up, let us say, nuclei. These are all things that we all know. And they in turn make up silicon dioxide molecules like so. Otherwise you won't have Silicon Valley and you won't have Sundar Pichai, but anyway, so that's silicon dioxide molecules. Now you begin to start seeing that this is the human scale. Obviously you cannot relate to a quark, you can't relate to oxygen nucleus either. Nevertheless, you can start relating to, let us say, silicon dioxide molecules, and a sand grain we all know, and the sand grains then lie on the beach over there. There are billions and billions and billions of sand grains, as Carl Sagan would say. And here is really and truly the human scale. Here is a human footprint. We leave footprints on the sands of time, as the poet said, which is lying over here on the seashore of this pale blue dot. How many here have heard this expression, pale blue dot? Well, that's fantastic. So we really are the pale blue dot, and this is where this institute dedicates its life to its activities, which is biology, right? Life is only there in the pale blue dot, as we all know. So the study of human life and biology and biological molecules takes place on this pale blue dot, as does climate change, atmospheric science, and all these things. And this in turn, of course, goes around this mid-sized star that is known as the sun. And here is Jupiter somehow shown to be larger than the sun, which is a bit silly. Nevertheless, that's the poetic license. And this object that's known as the solar system is probably one among millions and millions of solar systems, because today we know, and we didn't know this 20 years ago, that there are plenty of exoplanets which have been found, and now there is a whole catalog of exoplanets. Whether they form planetary systems or not, we don't know, but definitely there are exoplanets, and we know that some of them also have an atmosphere. And if there is atmosphere, what can you have next? You can have life. It's possible. Let's hope we have some cousins in some faraway exoplanet. Okay, not that we want to meet our cousins, but anyway. So let them be there. And this here is in the outer arms of this object that is known as the Milky Way. Okay, the Milky Way lies in, there are other galaxies also. How do we know there are other galaxies? How do you know? I mean, how did our ancestors know 3,000 years ago that there are other galaxies? Because there is definitely one naked eye galaxy. And which one is that? So actually, Andromeda, which today's children cannot see because all the cities are so polluted, you can't see anything. You can't even see Jupiter. I mean, forget about Andromeda, okay? But isn't that amazing that there are cousins like our Milky Way sitting out there? And we know it with our eye, but now we have all kinds of incredibly powerful telescopes. We know a lot about them. And this here is sitting in the local cluster of galaxies, which is sitting in this thermal soup, which is known as the cosmic microwave background radiation. The former president of our ruling party was named after it, Jagat Prakash Nadda. But that's a bad political joke. It's the first and last of my political jokes. Anyway, let's see. Just to make sure you're all kind of awake. Yeah. Did you hear the joke? Did you like it? Okay, good. All right. So I've been talking about science at the largest scales, right? The galaxies and cosmic microwave background radiation and all this kind of stuff, and black holes. What about at the other end, microscopic, really, really small microscopic world? Well, we had an amazing discovery in 2012, which was the discovery of a particle that we call the Higgs particle, whose existence was predicted in 1964. But still, it took almost 48 years for human beings to build a machine and build detectors and make sure that we are actually able to predict this. So now the way in which science is done is we call a press conference and we have a live streaming and the web and this and that, and then people come up and very solemnly say that they made a discovery. Very different from publishing in journals or, or sending these messages by pigeons and so on. So this said, and these words very German, so he said, I think we have it. Would you agree? He said as a layman. So this was the then Director General of CERN who made the announcement. And present at this event were two of the pioneers, Peter Higgs and also Francois Englert. There were many others who were associated with what we call the Higgs mechanism, but the Nobel Prize eventually was awarded to Peter Higgs and Francois Englert, although the paper was by Englert and Braut, but Braut had passed away, and so he couldn't get the Nobel Prize. So the paper due to Higgs and Englert and Braut essentially spoke about the Higgs particle, while there were others who also had the mechanism, but they didn't explicitly mention the particle. Well, life is tragic, but that's how it goes. But I want to say something about Englert and Braut. The paper was by Englert and Braut. Do you see any problem with the paper, the order being Englert and Braut? Englert and Braut, yeah. It's not an alphabetical order, right? So, and believe it or not, Englert was a PhD student and Braut was a thesis advisor. So that was a kind of error that was when the advisor would say that, look, the paper is going to go out with your name as a first author. I mean, these are really incredible. Not only that, Englert was also somebody who during the Second World War, he was during the Nazi invasion of Belgium from where he was, he had to be hidden somewhere and, So there is a human tragedy in everything that we do, human accomplishments and so on. These are all things that you may think this guy is rambling and saying all sorts of things. But in my opinion, to have a comprehensive picture of science, we also need to know these things. Who are these people, the individuals, what do they do, all this kind of thing. And it took so many generations of dedicated experiments at increasing energies to find the Higgs. And massive amounts of technology, superconducting magnets, all kinds of control of beams. In fact, this particular experiment has a superconducting ring which is 27 kilometers in circumference. That's the distance from here to Bangalore airport, right? Imagine a scientific experiment whose dimensions are of the order of 30 kilometers, and you have to control the orbits of microscopic particles using all kinds of, magnets, because these are all charged particles. And some of these magnets are also made by Kirloskar right here in Bangalore. So always have to bring in the Indian connection, yeah? So anyway, so just to say that science is an international effort, okay? So this is something that we need to keep in mind, that the era when people could really do these things all on their own essentially is not there. And India is also an associate member of CERN, and some of our scientists are working there, large number of institutions from the country where we are part of these experiments, okay? What do I do? So my own field is closely related to this. It's elementary particle physics, what I call field theory, and I study something known as a standard model of electroweak and strong interactions at high precision, well, at least I used to, until all my students graduated and left. So now I think I can go into a well-earned retirement, except that I have a new student now. So we have worked in many aspects, such as these contributions of pions to the muon anomalous magnetic moment. And I also have, last several years, been interested in mathematical methods to improve what are called Feynman diagram computations and use of computers. Feynman, has anybody here heard of him? This is finally one answer which is unanimous. Everybody has heard of him. Nobody's heard of me, but they've heard of Feynman. No. But anyway, so other applications associated with field theory are the things that I've been working on, planning for future physics at future accelerators. Here is an example of one of my recent papers, no longer recent, it's about 5 years ago. And this is a paper that was written with two former students, Shayan Ghosh, now works for industry here. Sumit Banik is now a postdoc at Stanford. Samuel Friot is a long-term collaborator from Orsay in France, who was an expert on objects that are known as Mellin-Barnes integrals. So these are all techniques that are also known to electrical engineers and mathematicians. And this is published in a journal called Physical Review Letters. Now this is a kind of journal that people would commit murders to get their paper in. Luckily, we didn't have to. However, the referee said that there's no way I'll publish this unless you share your codes with me, because I'm not really sure that the claims that you made are correct. So we had to rewrite the code and send it. And we think we know who it is, very well known physicist from Moscow. So he said, I tested the code and it seems to be okay, so I'll publish it, all right. So you see, also here, we are having to learn many things, computers, mathematics, physics, etc. And that's just the nature of the game. You just have to learn a lot of things. You learn something new every day, whether you like it or not. I'm not trying to scare you, just trying to say that this is it. And it could very well be a source of inspiration for you to do such things, okay? What good is all this? Have you asked yourself this question? We are all here at this, what is it called? The fancy Institute of Biological Sciences. I heard some such wonderful name. So if people ask, what is all this good for? You know, why are we spending all this public money? It's not the first time such questions are asked. This was asked of a person called Bob Wilson. He had to defend a project in front of a US subcommittee presided over by a senator called Senator Pastore. So Pastore asked him, what does this have to do with defense? So this was his answer, only from a long range point of view of a developing technology. Otherwise, it has to do with, are we good painters, good sculptors, great poets? I mean, all the things that we really venerate and honor in our country and are patriotic about. In that sense, this new knowledge has all to do with honor and country, but it has nothing to do directly with defending our country, except to make it worth defending. Beautiful speech, don't you think? Well, I'll tell you the bad news. The project was not funded. So, yeah. So that's how it is, you know. Many of the examples that I have given suggests that if you really want to do interesting and important work, then you require massive teamwork and technology, which of course countries do afford, but the way forward has been that now countries come together and form consortia and work together. CERN being an example, ITER is another, and I'm sure there are many in biology as well. No? A lot of science has been made possible because of advances in technology. The reason why Einstein didn't believe that gravitational waves would be seen, there was no device in his lifetime where such microscopic effects could be seen. So it's like you had these two laser interferometry, and this gravitational wave came and hit one of them, and then it shook this, and then the same wave went and shook the other one 3,000 kilometers away, and this laser interferometry detected this shaking of the fabric of the universe. Now, this requires extraordinarily high precision and technology and great stability and way in which you can minimize the noise and all sorts of amazing stuff, which is only possible now. It wasn't possible in his time. But then this immediately begs the question, what is my role if everything is so complicated? What am I good for? So rather than me answering this question, let us see what some great guys and gals have said about this, and what do the protagonists say about their calling, and what is the key message of all this. And I really don't have a message at the end of all this. I just leave it to you to actually weave the message and see what tangled web I'm going to weave for you. Okay, so one of the projects in science, of course, is always a struggle between reductionism and synthesis. We in particle physics, we are reductionists. We try to break everything down to the lowest possible. That doesn't work in biology because you work very complex systems, right? Of course, here you people are working with molecular systems, but if you take something like an ant colony, and some famous people like E.O. Wilson have worked, those are things which are fundamentally complex and cannot really be broken down to an atomistic level. And this is also one of the headaches of philosophy, is to figure out exactly what is what. But to me, it seems that what has happened in the past 100 or 150 years, there's been a super specialization. Every one of us lives in our own silos, barely talk to people in another silo. And so the key word that we are starting to see now is interdisciplinarity. which anyway existed before this era of super specialization. What do you call Newton? You don't call him a mathematician or a physicist, you call him a natural philosopher. Okay? So let's look at mathematics, which is one of the easiest things to think about, because especially in our country, mathematics is always taken as the ultimate bellwether of intelligence, right? So all kids grow up, he is very good at maths. So, but the thing about mathematics is at least you can explain this to anybody. For instance, if you look at this particular problem, which is called Fermat's last theorem, it's there written in letters of gold. So Fermat proposed that there is a problem for which there is no solution. Everybody here has heard of Pythagoras, right? Everybody here has at least passed 12th standard, right? So 3 squared plus 4 squared is 5 squared, right? So there are lots of integers which respect this. But the amazing, and this is as old as Pythagoras, it's probably known in all civilizations, because this is necessary for land measurement, right? It's obvious, right? You have the hypotenuse and triangle, and you have to make sure that land measurements are accurate. So I'm sure every single civilization knew about this. The obvious generalization of this, which nobody had asked before Fermat, which is about 400 years ago, is, do you have whole number solutions to higher powers, x cubed plus y cubed equal to z cubed? And you can search all you want, but you'll never find a solution. This was proved by Fermat himself. But he said that no matter what the power is, whether it is 3 or 87 or 4,000,008, there will be no solution. And this he wanted to, he claimed he had a proof, but today nobody believes that he actually had a proof, because it required essentially 20th century mathematics to prove that he was right. Okay? So there were many results on the way, proved in the 19th century, earlier parts of the 20th century, when partial results were proved, and it had been shown that if at all Fermat was wrong, it would only be for a finite number of cases. That's not, but eventually this was settled in the mid-90s of the last century by this person, Andrew Wiles, who had apparently read a book as a school child from his neighborhood library, where he read about this Fermat's last theorem. He was a highly accomplished mathematician, professor at Princeton, but he heard of some partial results, and then he again decided to prove that this is the case. It's an amazing feat of humankind, and this was based on some ideas going back to the 1950s by two people, Taniyama and Shimura, in post-war Japan. So you can imagine what Japan must have been like at the end of the Second World War. The country was devastated. One famous physicist, Nambu, who was also a Nobel laureate, actually has written somewhere that he used to often go to bed hungry, and then he would sleep on the tables in the laboratory because he couldn't afford to stay anywhere. So this is not to say that suffering is either a necessary or sufficient condition to do great work, but just keep in mind the kind of odds that people have to, suffer before, they can make great contributions. It's also humbling to think of it, For instance, I complain like crazy every time the power goes off for 3 minutes. I just curse IISc, can't even keep the power supply. Then I remind myself of Nambu and Taniyama and Shimura, and I kind of become a little more sober at the end of it. So this is a kind of thing, and there's a beautiful book by Simon Singh on this proof, and Andrew Wiles also describes his eureka moment in a BBC interview of how he came across this result. It's something that I strongly recommend that you watch his BBC interview. Okay? There's nothing to do with mathematics, there's nothing to do with Fermat, but just the human spirit and how it actually prevails in a variety of cases. So here's another example from mathematics. Of course, mathematicians are well known to be kind of unusual people, if that's the word that I'm groping for. What would you use for mathematicians? So he's too nice to say anything. Okay, so anyway, so here's another example. So he proved a conjecture due to Henri Poincaré from the beginning of the 20th century about properties of surfaces in 3 dimensions and how they are connected. So this person pictured over here, Gregory Perelman from St. Petersburg, he actually also plowed a lonely furrow, and he actually proved this particular theorem. But as I said, mathematicians being mathematicians, he refused the highest award in mathematics, which is the Fields Medal, and he also turned down the prize of $1 million. So people like this, I think, add to the romance of mathematics, which is what attracts a lot of, shall we say, strange people to mathematics. Okay. So let me also dwell on this idea of interdisciplinarity and how subjects come together. So there are problems that I just described which are essentially in mathematics, and they did borrow from some other fields, but today we have other subjects like theoretical computer science, which is essentially mathematics but has a tradition of its own. But there are problems in theoretical computer science which needs methods from mathematics to prove, or also from physics and so on. So here is one such problem. It was an outstanding problem in quantum mechanics for a long time, which could have been restated as a problem of infinite dimensional matrices. And this was proved recently by 3 people, Marcos, Spielman, and Srivastava. So Srivastava was then, he was working in Microsoft here in Bangalore. Now he's moved to Berkeley after that. So this problem which arose in quantum mechanics turned into a problem in computer science, which was then solved by these people. Do you see some familiar name on this? Everybody has heard of Feynman. Have you heard of this other person? Ramanujan? Yes? Great. Unanimous? Everybody? Yeah, great. Now, Ramanujan died in 1921. How could he possibly have had anything to do with this problem, which arose in the 1950s? So that was the power of his ideas. It was so incredible that there are objects named after him that came in handy to solve a problem in theoretical computer science which had its origin in quantum mechanics. Now, this is all really incredible. No? Of course, Ramanujan, the only word that I can find to describe him, is really a freak of nature. He's just so incredible that nobody can really understand where he came from. And needless to say, there's been nobody like him after that either, right? So here is a person self-trained. Of course, he was assisted by a community in Madras, went to Cambridge, and he was passed away by the age of 33. You know? But those ideas are so far-reaching that they are of great importance even today. Now, I shouldn't give you the impression that all great ideas and inventions are only in physics and mathematics just because I happen to work in allied fields. There are amazing discoveries. The periodic table of Mendeleev, just imagine taking all the matter in the universe and organizing it into one table which hangs in every single library. This, to me, is one of the very great accomplishments of the human mind. Does everybody here agree? Yeah, yeah. You have to agree, otherwise I'll just drag this talk on for another 2 hours. You know? So just think about the theory of evolution. I mean, what an amazing feat that is. You know? Of course, human beings are aware that things change and all, but whether this actually has any scientific basis, I mean, it took essentially Darwin, probably Linnaeus, some others, to really understand this and put this in perspective. Now, of course, Darwin traveled to faraway Galapagos Islands, and then he studied his finches, and he looked at tortoises and so on. But today, I believe that you can actually see evolution essentially in real time, whether it is in the laboratory with fruit flies with 4 chromosomes, or whether in Madagascar, which is considered to be a petri dish for evolution, because there are valleys which are just separated, and you can see the evolution of species going on simultaneously in neighboring valleys, and then you can figure out how species are diversifying. Isn't that amazing? I also, not that I am an expert in the subject, consider Mendel's theory of genetics to be totally amazing. You know, of course, people say he didn't use proper statistical methods. Statistics did not exist as a discipline at the time of Mendel. So how does it matter whether he used it or not? But he was actually able to use controlled experiments to show that there is a genetic basis to evolution. Now, isn't that amazing? We all know that we inherit our traits from our parents, and I, of course, conveniently blame all my deficiencies on them. It's very handy to have this genetic theory, but to show that this has a scientific basis, it's an incredible discovery. Or Pasteur's theory of microbes, that beer and diseases have the same origin. Isn't that amazing? I think so. Anybody here disagrees with me? This shocked silence means that they all agree with me. There are also other things like Shannon's information theory. Think of continental drift. You know, today we know we can cut all the continents out of a map and put it together, and it does look like there was a Pangea at some time. But imagine the first person who had to do that. You know, that he could actually somehow prove. He couldn't really prove it in real time because the scales of time very different compared to human life. This is a great one. I think Alfred Wegener was his name, continental drift. And then the theory of ice ages. Imagine what a beautiful idea that is. Milankovitch cycles. This is something that I only discovered rather recently, you know, during my reading. It's what controls long-term weather cycles, and this has to do with the various deformations of the Earth's orbital tilt and the nutation of the Earth's axis, and also the eccentricity of the orbit. Now, who would have thunk that it's possible that Jupiter far away can actually affect your human life? Astrologers would, but this is also true scientifically, that, you know, the Earth's eccentricity is modified by Jupiter. And Milankovitch also predicts the periods. There is a cycle which is 40,000 years, another cycle which is 100,000 years. And biology, of course, the most romantic story. Unfortunately, I know only a very old book which is called The Eighth Day of Creation, which brings to life all the characters of modern biology, such as Max Perutz, Max Delbruck. Probably you have to be named Max to be a very famous biologist. But anyway, once again, I should not give the idea that everything is done by men. We do know that women have been oppressed for a long time. This has to do with evolution, with human history, systematically denied opportunities, confined to home. But anthropologists will tell you that things like agriculture, metallurgy were all invented by women, which is highly plausible hypothesis. You can look up God and Child, if you like, to see some discussions around this. Also an old author, I'm sure there are many more. But in the modern world, we have Ada Lovelace, who was a daughter of Lord Byron, the poet, who's considered as essentially the founder of modern computer science. Emmy Noether, the very famous mathematician, died young. That seems to be another necessary and sufficient condition to be a famous mathematician. So clearly I have lived long, so I'll never be very famous. So as founder of modern algebra, all of you know about Marie Curie and the discovery of radium. Now, why have I mentioned this person? Which one of you was awake on slide 2? Yeah, all of you. Okay, so this person was Cecilia Payne, and she is not very well known, and she should be known. She's the one who was able to kind of figure out the abundance of elements in stars, okay? Something that fundamental, that basic. I'm told that before her work, people thought that the abundance of elements in stars was similar to what it is, let us say, on Earth. It's not true. She proved that it's mainly hydrogen and helium. And you'll be happy to know that helium was discovered in India. Did you know that? How many of you knew helium was discovered in India? And why so? Well, helium was found in the sun, named after Helios, and India is a hot and sunny place. That could be one reason. But no, there was a total solar eclipse sometime in the 19th century, and a French astronomer came here and did the spectroscopic analysis, and he discovered in Guntur or Machilipatnam where the path of the moon's shadow went. Okay, so that's our contribution to biology. To astronomy. I'm sure there are many more. We have astrosat, we have all kinds of contributions, but helium definitely belongs to us. So Julia Robinson, another famous mathematician, she solved a problem that was known as Hilbert's 10th problem. Does anybody remember the name Hilbert? From slide 1, yes. So Hilbert was such an influential mathematician that at the first International Congress of Mathematicians, he posed 23 problems. Why not 22? Why not 24? We can't ask him, he's not here anymore. So many of those problems to date are actually not solved. Some got solved immediately. But one of them that was hanging around, which could not be solved, was known as the 10th problem. And this was solved by a woman, Julia Robinson, along with some Russian experts. and she showed that this problem is also undecidable in the sense of Gödel. And each time I give a talk, and I'm a one-man traveling circus, gave this in Calcutta, somebody came up to me and said, your list was incomplete, you have to add Catherine Lonsdale, who figured out something to do with the structure of benzene. But benzene's structure had been, the original one was discovered by Kekulé, as you know, about the snake eating its own tail. Okay? Many, many more women, so it's not like I'm doing a census of women, but each one of these is an important person that at least 50% of the audience should know, and please try to educate the other ignorant 50%. Okay? Vera Rubin is the discoverer of dark matter, one of the most important paradigms in physics now. Jocelyn Bell was the discoverer of the pulsar. How many of you heard of Jocelyn Bell? She's very famous also for the wrong reason, because she was somehow unfairly denied the Nobel Prize for the discovery of the pulsar. During my long suffering as the chairman of the Center for High Energy Physics, there was very little compensation. The only compensation was I got to have lunch with Jocelyn Bell when she was visiting, but the lunch was no good. Don't tell anybody. Yeah. So, of late, we've had two Fields medalists among women, first time in history, late Miriam Mirzakhani and Marina Vyazovska. It's kind of amazing, a prize that is 100 years old, the first time women are winning. But of course, it also means that women are entering in larger numbers into all these fields. And for the longest time, there are only two physics Nobels for women, Marie Curie and Marie. And Maria Goeppert-Mayer, just like to be a biologist, you have to be Max. To be a physicist, woman, you have to be Marie or Maria. No, it's not true. So Donna Strickland and Andrea Ghez are recent Nobel Prize winners. Do these names mean anything to you? Jennifer Doudna and Emmanuelle Charpentier? Anybody? This is NCBS. Come on, you people should know. You know? Well, they also, you, my gentle host. Yeah. So they were Nobel Prize winners too. But what was special about that particular Nobel Prize? It's the first time I think two women were awarded the Nobel Prize, and only two. There wasn't a third. I consider that a landmark. Of course, you may say this is political, this may be this or that. Of course, we are all human beings. There's no human beings without politics, and there's no politics without human beings. Now, Nobel Prizes are going to engineers, okay? AI, ML, you know, quantum, this, that. That's how it is. The world is driven by commercial interests and industry, academia, it all comes together. That's how it is. And some other women that I wanted to mention, Bibha Chaudhary, she's did some very important work in 1935 and was probably on the scent of a particle that's very important called the pion, using cosmic ray experiments, but she's not terribly well known. I'm going to pause for 2 seconds and drink some water, and I want you to spot what is odd in this last entry over here provided. You can read it. Everybody can read it? You didn't bring your opera glasses. Rosemary Fowler and discovery of the kaon in 1948, awarded honorary degree by the University of Bristol in July 2024. Any anomaly you detect over there? That's right. And it's totally amazing. She went to receive her degree 75 years after its discovery. She went on, had a family, this and that, but her contributions were recognized a little late. Better late than never. This also means that although mathematics may not be good for your health, physics is definitely good for your health. So anyway, here are Doudna and Charpentier. So this ought to be a source of inspiration for men and women, of course, needless to say. And these are these other ladies I mentioned, Emmy Noether, Mariam Mirzakhani, and this is the outgoing Director General of CERN, Fabia Gianotti. She had 2 terms as Director General of CERN and stepped down on December 31st of 2025. Since this is NCBS, I have to mention an extremely important biologist whose centenary year has just gone by, and he won the Nobel Prize in 1968. And I'm sure I don't need to educate you about his contributions. This was Hargobind Khurana, and he's probably not a terribly well-known figure, kind of aloof, won't you say that? He's never in the public eye, and nobody really knew much about him. But still. What about Indians? I have now been talking about people from all over the world, men, women, etc. What about us? Are we good for nothing? Well, of course, we are harshly critical about ourselves, but it should also be an opportunity to say some nice words about ourselves. Jagadish Chandra Bose, this was also added by my friends in Calcutta after my talk. You left out Jagadish Chandra Bose, so he's been given the first place now on my list. So Ramanujan, of course, already mentioned Raman, very well known. Saha, Bose, all well known names. Homi Bhabha, Vikram Sarabhai, Prashant Chandra Mahalanobis, who founded ISI. Then there's famous A.K. Raichaudhuri, whose equations were needed to establish existence of black holes and relativity. G.N. Ramachandran, of course, I don't have to say anything about him. And Yellapragada Subbarao. How many of you here have heard of Yellapragada? Rather small number. He ought to be known much, much, much better. Fundamental contributions to medicines. All kinds of deadly diseases. And if you read Siddharth Mukherjee's Emperor of Maladies, he talks quite a bit about the work of Yellapragada Subbarao as one of the pioneers of chemotherapy. And we don't know anything about him. There are others, Birbal Sani and Janaki Ammal, who's, I saw a picture of hers or a bust in ISER Pune. So at least now she's being recognized. And we have very great mathematicians. Ram Prakash Bamba, he just passed away at the age of 100. So that contradicts my theory about mathematics not being good for health. But anyway, so this is the exception to the theory. Sarvadaman Chawla was a very famous mathematician. Harish Chandra, one of the greatest mathematicians of all time, perhaps, who's totally unknown, except that there's an institute in Allahabad named after him. He's an alumnus of IISc. Many others, George Sudarshan Abdul Salam, they all came from here. C.R. Rao, again, 102, not just 100, that was the age he reached. And I refer you to all these nice books by Venkatraman on various Indian legends. But then how do the minds of scientists work? What is it? Is it an arbitrary thing where you can do whatever you like? Or are there rules? Are there standards that you have to meet? It's not a question that I have posed. It's been posed by everybody. When we say something is scientific, what does it mean? Scientia itself, the word means to know, right? Knowledge. And to know something means that something that I know and I can convey to you and you can check for yourself. Given a particular era, given the limitations at that time, we all have to agree that it's right. Others have thought about it too. There's a book called The Mind of a Mathematician by Jacques Adamar, where he has gone into these questions. And Helmholtz has also thought about it. Helmholtz, how many of you here have heard of Helmholtz? In what context? Coil. He's heard of a coil. How about you? Okay, there's a Helmholtz equation. There's a Helmholtz free energy. Although there's nothing free in life, he's got a free energy named after himself. But he also invented the ophthalmoscope. It's the same Helmholtz, not his son or uncle. So imagine in this 19th century, there are these people who did all these things. They were great universalists. And he found time to do a bit of philosophy also. I guess his wife must have been doing all the cooking at home while he was doing all this. Don't tell anybody. Okay, so they figured out what really should be the basis of science. So they say the ideas, for you to be able to incubate an idea, it requires some preparation, which is obvious, right? To think about a problem, you have to figure out where you stand, all these things, and then you may get the solution, but then it has to be followed by verification. Unless you do all these things, it is not a science. If you don't verify something or falsify it, it cannot be considered scientific. So there are again very classical examples of Max Planck. Planck, anybody heard of him? Planck, no? He's founder of quantum mechanics. So he first wrote down a formula, but it took him some time to figure out what's the kind of theory from which it comes. And he's also talked about it. So he, after finding his formula, he was able to figure out that there has got to be an underlying theory for his radiation formula. Henri Poincaré, whose name I had already mentioned to you earlier, he's been described as one of the last universalists in this famous book by E.T. Bell, Men of Mathematics. So what made him universalist is he didn't believe in various sub-disciplines of mathematics in his time. He also contributed to physics. Today you have an algebraist, you have a geometer, you have a number theorist, you have an analyst. Nobody is really a mathematician. Similarly, I'm sure in biology there is a splintering along these things, which of course is unavoidable, because if you have to become an expert, you have to choose a domain. You can't be a generalist to the extent of being a bullshit artist. Oops, please expunge those words. So, but that said, you can't lose the big picture either. So, to that extent, Poincaré is considered as a person who contributed in many fields, differential equations, founder of topology. He also was on the ascent of special theory of relativity and so on. So, he was a person whose vision was not very good. So, he had to do a lot of his thinking in his head because he couldn't see very clearly. So, in his mind's eye, he had to figure out things. So, he is said to have described his eureka moment when he was stepping onto an omnibus, how he found the solution of a problem that worked on him. So, it's flashed upon him. Such moments, I think everybody in their scientific career experiences or hopes to experience. These are also called epiphanies in religious experience. So, this is, when I speak of joy of discovery, it's also the hope that, you got it, as in the water purifier eureka moment. Yeah, so, sorry, people are getting tired. I should wind up a little bit. So, here are other examples. Dear me, 5 minutes. Examples of eureka moments. Kekulé, who I mentioned earlier, talks about how he figured out the structure of benzene as a snake gobbling its own tail. Now, nobody really knows if this is true. Certainly makes a nice story. So, Max Planck also talked about it, and he says the outside world is something independent from man, something absolute, and the quest for the laws which apply to this absolute appeared to me as the most sublime scientific pursuit in life. Now, unless you have this kind of a commitment or this kind of a resolute belief, it's hard to really survive in science. Really making it sound like it's an impossible thing. This is just a warning, just a caveat. So, scientists of course work very hard for the moment which may or may not come. So, I have had a couple of these also, but I'm not going to tell you about them. Go back and read. Shouldn't make this so selfish. So, how does one go about science? Is it just like digging a hole and just working very hard, or does the work have to make sense? Does it have to work within a framework? Does it have to have concrete goals and milestones? Of course, there have to be. So, I shouldn't be just quoting old fogies such as myself or older. I should also quote somebody much younger than myself. And this Nikhil Srivastava, who must be just 40-ish, gave an interview to some newspaper, and he says, he's the same Srivastava I mentioned earlier, does not believe in being a mega workaholic, but he believes in short spurts of focused, high-quality work. It's very nice, which young people can also keep in mind. There's something known as a Pomodoro method. Pomodoro, you all know, the tomatoes. Yeah, so you can Google that and find out. I have not necessarily applied it to myself, but apparently it works. So, he says productivity in deeply thinking about one problem for weeks or months and then taking time off, because the mind needs rewire, start seeing connections that it didn't have earlier. And he also says, and this is something that I had not thought of earlier, you should fail in different ways, but if you know you've tried everything, you're still failing the same way, you may have to give it up, which is kind of sobering, but probably worth keeping in mind. Venki Ramakrishnan, well known to you all, also has this to say, that it takes courage to tackle very hard problems in science. Okay? And he does not want science to be converted into a contest. This I agree with. I mean, all these kinds of hackathons and all these things, in my learned opinion, are not very nice. You have to do it for the sake of science, not like a running race, not at all pleasant. But his father, who was also a biochemist, said of his son that it was a great advantage for Venki Ramakrishnan that he had training in many different fields. I think his PhD was in physics, then he did a course in biology, and then got his Nobel Prize in chemistry. He was constantly mixing various things. I believe that there is some merit to that also. And I'm not saying you have to keep jumping every 2 years from one thing to another, but if it so happens that you have moved fields and all, always use it as an advantage, because some problem solving that you've learned in some field may come in handy in another field. It's also been true in my own experience that really helps to have had, but there's no escaping from pretty hard work. Weinberg, the Nobel Prize winner in my field, so he wrote 4 golden lessons. So he says no one knows everything, and you do not need to know everything to start your research. Okay, so this is, how many of you here are students, PhD, IPhD, etc., etc.? Yeah, okay. So please keep that in mind. You don't have to know every single thing. Okay, just start your research. It's like reading books on swimming. How many of you have read books on swimming? There's no point reading books on swimming, right? You have to go and jump into the swimming pool over there. Yeah, so it's like that. Just start doing it. Okay, you will learn on the way. And he also uses the same analogy as someone else did. Aim for rough water. You know, these people, these maritime allusions. What he says here is, don't just work on incremental research. This is what everybody makes this observation. Try to work something new. Of course, it's risky, and you may waste time on a problem which doesn't get solved, but that's life. And this is Weinberg's address. Oh my God, learn something about the history of science 25. About the history of science. This everybody may not agree, especially your advisor will not agree with this, because he or she will consider this a waste of time. But I kind of agree with that. Last few words, because this has many students here, is science and communication. In my opinion, communication is very important. A very good idea and so on, and you write a lousy paper, nobody is going to read it. Okay? And you have to put yourself in the shoes of the reader and really convey, yeah, got it, yeah. So practice writing papers. This is also the era of social media and so on, and don't be shy of disseminating your work using social media, and communicate properly, get along well with your fellow researchers, and in my opinion, this is going to continue to be more and more important. Also, in my opinion, and NCBS, I think, has taken a lead in many of these things, is we also need to communicate with people in other spheres of human life. Don't stay in your silo. It'd be nice to know how artists create, how poets create, how performing artists create. And in fact, you'll be amazed at how much, you know, sculptors and all these people know about chemistry. They'll know if you mix this with that and bake it at 1000 Celsius, you get that color, etc. So don't think that people who are in other fields don't know what you're talking about. There's a lot we can learn from them. And today I feel that every one of us has to go to the computer to help to improve our creativity. And as this is something I said right in the beginning, you cannot avoid cognitive stress. There's just no way you can avoid that. And these are things that I don't really need to say. Today we have so many institutes where so much work goes on, except that very few in our country actually talk about what they are doing. You know, we are always looking at Feynman, we are looking at Bob Wilson, we are looking at Jocelyn Bell, but what about us? Do we convey what it is that we are doing? There are very few examples of people in India who do important work, who actually tell others what it is that they did, how did they get to that problem, how did they address it, how did they solve it. One counterexample was this very nice description of the work done more than 20 years ago by Agarwal, Kayal, and Saxena. They solved some important problem, theoretical computer science, primality testing. Frontline and others wrote very nice articles. And one of my former colleagues, late Professor Anil Kumar, teacher of Ranabir Das over here, he has written a very nice essay where he talks about one of his fundamental discoveries, which is called the nuclear Overhauser effect in biological molecules. He was an extraordinarily humorous person. So he was working in Zurich as a postdoc, and he said that the place was uphill, and the Swiss would always walk uphill and then take the bus downhill, unlike Indians who would do it the other way. So over the Christmas, New Year break, nobody was using the machine, so he got 10 days of that machine to himself. And that's how he did the analysis, and how first it didn't make any sense, and he had to run it again, and made this pretty amazing discovery. Have you read it? Did I quote it properly?
Yes.
Okay, thanks. Okay, so my last bit of advice, since I'm now a senior citizen, I can give lots and lots of advice to people, not that they're going to listen to it. So follow your hearts. Nothing is more fun in discovery, because without you, there's going to be no tomorrow. I mean, society will just be static. Young people don't participate, and there's no science, no research. That's the end of civilization, you know. But it requires a lot of patience, like running or even sprinting a marathon. Yes, unfortunately, it's true. Thomas Edison, how many of you heard of Thomas Edison? Have you seen this quote? He said it's genius is 99% perspiration and 1% inspiration. I think he was wrong. It should be 99.9 and 0.1. But anyway, so also I refer you to an amazing article. There's a written transcript as well as on YouTube. It's called You and Your Research by Richard Hamming. Write that down, You and Your Research. Okay? Just like Patrick Winston's How to Give Talks, there's another one that I refer you to. So he has a lot of tips on how to do research. And this has actually had an impact on me, you know. There are many, many things he says, you know, don't try to fight the system because you won't win. You have to take the system with you. Learn to get along with people. And he says you should also keep your mind fresh. You should move to problems every so many years, collaborate. Amazing stuff. And some may say, oh, I need luck. Oh, unless I don't have luck, I'm not going to get anything done. But then you need a definition of luck, right? So I'm not going to be the one to define it, because it's already defined 2,000 years ago by Seneca the Younger. So luck is what happens when preparation meets opportunity. Isn't that amazing that he gave? This is a timeless definition of luck, which I like very much. So let me end, because I'm here at the NCBS, with a quote from one of the greatest biologists of all time, Charles Darwin, whose name is again letters of gold. So he says of his own theory, there is a grandeur in this view of life, with its special powers, while having been originally breathed into a few forms or into one, and that whilst this planet has gone cycling on according to the fixed law of gravity, from so simple a beginning, endless forms more beautiful and more wonderful have been and are being evolved. And I finish now with the words of David Hilbert, which I began with. This time in German sounds so much more noble. Wir müssen wissen, wir werden wissen, which of course means we must know, we will know. Thank you.
Thanks, Anand. That was very nice. We'd like to hear from you on this, thoughts, and open for discussion.
Unless there are 25 questions, you can't get out. No coffee. Yeah. Come, you're not the shy type. You're in the best institution in the country. You must all have minds of your own, ideas of your own.
Hi, good evening, sir.
Good evening.
A wonderful presentation, very refreshing, especially as you said in these dire times. I often think, why am I doing what I'm doing? So anyway, a few questions that came into my mind are from your own field of work. So I'm doing my first year of masters, and what I am interested in looking into right now is dimensionality of free space by the interference of gravitational waves, and where this particularly comes into play in your perspective is, since you are also working on field theory, I also intend to look into a bit of graviton and gravitational waves correlation, because each and everything has a particle and wave characteristic correlation going on, right? And that's where everything stands out. In order to work on this, do you have any suggestions that I could go forward with? And then also, apart from which, one more thing that came into my mind was, just yesterday we were having a class on quarks, and I asked my ma'am what does she think about does she think about ghost particles, right? And graviton essentially is also one. She said since there is no proof, it doesn't really make sense to me. That I don't honestly believe in it until I read a proper establishment of it. What do you think about that?
Yours is really a multi-part question. Um, so as far as wave and particle, yesterday we had this amazing talk by Ananthanarayan, who also is a member of the science writing activity here at NCBS. So he is a very famous science writer, has written a book on this topic. Probably it'll be up on YouTube of our center very soon. So you can just listen to that. He's also written a book, something about two-slit experiments, a beautiful book. So this is an issue with quantum mechanics which we don't really consider as a paradox. Okay? Nobody really considers that life is like that quantum mechanics is that way. As far as gravitational radiation is concerned, most of my work is at energies where you'll have no sensitivity to any kind of gravitational interactions. But my good friend and senior colleague Subendra Mohanty, who's retired from PRL, has written a very nice book, Lecture Notes in Physics on Gravitation, Gravitational Radiation and Particle Physics. I would just refer you to that book and you can just see there rather than getting all kinds of wrong information from me. Okay? As for graviton, we expect that there should be gravitons which are quanta of the gravitational field, but we have no way to detect them today. Maybe 100 years from now, or if people like you design some wonderful experiments or sensors, maybe we'll see them. You know? So these are, we don't want to answer every single question, then what will there be left for you to do? Okay?
So we'll maybe take one more question, then there is tea outside, and then I'm sure you'll be happy to
Fine.
have
Yeah.
more discussions.
Yeah. Now there's one more here. We can take hers also.
Okay.
Hi, sir. My
Hi.
question is, so once we become, let's say we are PhD graduates and we do our postdocs, we come back to the country. Some of us end up in academia. Some of us might join organizations like ISRO, DRDO, and all the other big organizations. I wanted to know, you mentioned something about not fighting the system, but these systems are very rigid, and for a young person, they are very misfit. So I just wanted to know, where should we place ourselves in such systems? Should we fight it or should we leave them?
But we need not assume that everything in life is a fight. You know, all of us live in society. We all have to follow certain rules. We don't immediately feel that we are somehow besieged. You know, we don't have to think that way. And I don't know, in my opinion, organizations like ISRO and DAE are very successful organizations. And you know, there is a discipline associated with organizations that somehow are responsible for the defense of the country or building the country and so on. So it's not like a hobby, right? So something like DA is an extraordinarily sensitive organization. It deals with atomic energy, and it deals with fissile materials, and it deals with energy, and it deals with radiation hazards. The reason why all these rules are in place is to make sure that nothing goes wrong, right? We've had an accident at Fukuyama. What is that place? Fukuoka, thank you. Or at 3 Mile Island or Chernobyl. We haven't had anything over here. We should be glad, right? So even though Kalpakam had some event after that tsunami, nothing happened. So every organization in the world will have rules. Think about working for Lawrence Berkeley Laboratory in the US. Those are all hyper secret organizations. So that's life. Okay? So if you want a good job and a good income, there's also responsibilities that go with it. That's my opinion. And I wish you all the best, the PhD postdoc. It's all fine. Take it easy. It's not even possible to predict 1 week into the future, you know, what may happen. Why do you worry about that? The world may change after that, right? There's no way in which we can predict. Just scale back the anxiety a little bit. It's a valid one, but every person, every human being has to go through this. Whatever you're going through right now, I'm sure Varada went through 25 years ago, and I went through it 40 years ago. That kind of dates me, but anyway. So that's life. Did I answer your question? Yeah, somewhat. Yeah, no, you shouldn't be satisfied.
Okay.
The young lady here had a question.
Thank you so much for that insightful talk, sir. It has opened up a lot of point of views for
Thank you
me.
so much.
I'm doing my project right now, and I recently discovered that even a negative result is a part of the experiment, and there are a lot of rejections I got when I had applied for academic internships and such. So, as a scientist, what is your advice, or what do you want to tell young people how to deal with these rejections in science as well as the negative results that can come up during experiments?
I hope I didn't give you the impression that I had only positive results my entire life. It's not like that, you know. Everybody has gone through innumerable rejections, you know. After I finished my PhD, I actually kept a stack of rejections until one fine day I said, how stupid can you be? Just throw them into the dustbin, okay? So that's how life is. It's like anything else you do, right? I mean, just have to deal with it. You have to keep exploring your opportunities. Just let me tell you, there's a very famous professor or scientist now in Australia of Indian origin, Chennupati Jagadish. He's a great guy. He must be about 70-ish now. He's got the highest civilian award of Australia. I think he's called something or the other, like our Padma Vibhushan. India, we have so many, they have only one. So he's got the highest one. He's a fellow of every single academy in the world. So he has written about his life. Comes from rural Andhra, where there was one teacher who would invite all the poor children to come and stay in his house, and then he would teach these children, and then they would have to walk in kilometers to school. He did his PhD in IIT Delhi, I think. He said he had more than 300 rejections until he got one break in Canada. From there he went to Australia. He is the most humble, most approachable persons you can meet. Chennupati Jagadish, can you remember that? Yeah, write that down. Just Google him, and then that'll tell you something, okay?
All right, so thank you again, Anant. That was
Thank
really
you.
fabulous.
Thank you, everybody.